talk about Mantle. So today, I really want to talk about three things. First, I want to explain what Mantle is and why we're doing this. A second thing, we would like to cover some of the most interesting features that make it a very compelling platform for everybody. And the third, probably the most important thing, why does it matter to you? What does it bring to developers? So the first, the most important question, what is Mantle? The short answer is that Mantle is a graphics API. Likely you already know that. There's, of course, a long answer as well. And the long answer is that Mantle is all about innovation. Right? Now, let me make it very clear that this is not about innovation for the sake of innovation. And we are not really trying to invent some alien technology. What we are trying to do is to remove the obstacles. And those are the ones that I've been talking about when I did my introduction. Those are the ones that are blocking developers. And what we would like to do, remove those obstacles and let their innovation flourish. Now, you have heard from the initial announcement that this is a low-level API. Now, what I would like to explain is that thinking of API as a high or low-level API is just a wrong way of thinking about something like API. The way you would like to think about it, is this the right tool for your job? And what we are trying to do with Mantle is to give the developers the right tools. And we do that by adjusting the abstraction level. We are trying to do it so the abstraction level is such that it's just right. Sometimes we do that by lowering the abstraction level where it makes sense. Sometimes we even raise it up a little bit. We don't want to lower the abstraction level across the board because we would like to be able to innovate and change our architectures and support that with Mantle for the years to come. And possibly even allow our competitors' hardware to be supported with Mantle. The other thing that we are defining is the feature set. We are drawing a line in the sand and saying that we're going to support a feature set for the modern GPUs. The GC and the graphics core next architecture that is present in some of the next-gen consoles and a large portion of the PC market is the foundation, hardware foundation for Mantle for us. Now, the next important question that you probably have is, why Mantle? Why another API? There are actually a lot of reasons why. And I'll cover only some of them, because this might take me a day to go through all the reasons. Okay? But the first, the most important one, why it's a new API, is because the new API allows to do a lot more. The existing APIs, with all the tweaks, can get you only so far. And this is not what developers have asked us for. And we worked very closely with DICE and other developers to define real-world problems that we wanted to solve with Mantle and define how those solutions can come to life. And what developers wanted was a couple of things. First of all, fixing their performance issues. And second, getting out of their way, giving them control over the GPUs, because they can do a lot of good things with that. There's actually a lot of excitement, as you can see, building inside of AMD as well as among the developer community. And I want to make it very clear what we are doing is really trying to first answer the developer requests, but also we would like to kick it up a notch for the whole industry. Right? There's a bit of a stagnation, unfortunately, for the last couple of years. We would like to get everybody energized again and excited again with the new, fresh, cool API. Now, I have to make sure that you understand this. We are not trying to please everybody with Mantle. You know what? Maybe this is not the right solution for you. It's not for you if you do not care about performance. It's not for you if you don't care about taking the ultimate control over PC platform today. It's not for you if you don't care about bridging multiple platforms with a minimal effort. So the choice is yours to make a conscious decision, you need to understand what the trade-offs are. We give you a lot of control and power, and as cliche says, with great power comes a lot of responsibility. So now you do have to be worried about a little bit more, just like on the consoles, right? You need to be aware of some extra things. So things potentially might become a little bit harder, but I'll give you an analogy. It's like driving a car with a stick shift. It's a little bit harder than with automatic transmission, but at the same time, a lot more fun. So if you like driving, you drive stick. It's that simple. At the end of the day, it's all about performance. So we've tried to make a solution that is the fastest API, graphics API ever. We've put a lot of features, and the core really is on improving performance, first on the GPU side. By bringing you closer to the hardware, we give you ability to extract a lot of GPU efficiency. But that's not all. We're giving you a lot of performance-related features to unlock all this performance on both CPU and GPU side. Some are generic, others are more targeted at GCN architecture. And while we're making GPU efficiency improvements that are great, we'll blow your socks off in terms of CPU utilization. And I can tell you that this small batch problem that developers have complained about for the last 10 years or so is now a thing of the past. So let me quickly go over this small batch problem and explain what it is. How many of you know what it is? So for the rest of you guys who are not familiar with it, let me explain that. Right now, if you run your game, you start hitting a wall in terms of performance once you render so many draw calls per frame. That becomes a bottleneck. And that number today is roughly 3,000 to 5,000 draws per frame. This is what every year you would hear from us at AMD and other HV vendors at GDC optimization talks. In fact, when I was doing DevRel work, every year I would come in at GDC and hammer this message, 3,000 to 5,000 draw calls. Now, if you're an amazing developer on a lucky day, and I know only a couple of games that can do that, you can do probably 2 to 3 times that. Now, this is great, but the goals we have are a lot more aggressive. What we would like to do, and this is our target for Mantle, to give you at least a magnitude better small batch performance. Not 2 to 3 times, a magnitude better performance. 100,000 draws per frame, or maybe even more if you optimize further, because we also give you a lot of controls for additional optimizations. And this is really groundbreaking and game-changing. And again, I can probably talk quite a bit more about this, what it really means for the industry, but we'll leave it for some other conversation. Now, there are certain issues that we are trying to address, very practical issues that are based on years of our experience optimizing drivers, working with the ISVs. So I'd like to go over those issues with you here. First of all, it's an API overhead. The drivers today with existing APIs are not all that lean and mean. There is no direct way to translate the API commands to the GPU commands that are natively understood. So one thing we are trying to fix is API overhead. But even just fixing the API overhead would not give you the very aggressive targets that we've set for Mantle. The key to today's performance is multi-threading. And if you think about it, all of us have many core CPUs, 4, 6, 8 CPU cores. And most of those cores are not accessible to driving graphics. This is wrong, and we can fix this. Then memory management on PC kind of gets in the way as well. If you look at the consoles, with a much smaller memory footprint, they're able to achieve greater visuals than PCs with comparable, even slightly bigger memory. Again, this is something that can be fixed, and this is a very important component of making a very fast and efficient API. And the last but not least, lack of direct control over GPU sacrifices CPU efficiency, GPU efficiency, as well as prevents us from giving you predictable performance, behavior, and very well-controlled latency. Now, since we were starting from scratch, we started from a design philosophy. And at the foundation of it is simplicity and features. Features carefully selected to give you what you care about the most, performance. Because as I said, at the end of the day, it's all about performance. Now, simplicity, don't make a mistake. Simplicity doesn't mean you have to sacrifice features. Simplicity means that we very carefully generalize what we can at the API level. As Einstein once said, make everything as simple as possible, but not simpler. And that's exactly what we are doing. Simple API is a beautiful thing because it gives you predictable performance and behavior, and this is something you can understand. And this is precisely what developers wanted. And all the features, really we are targeting a very concise feature set. Those features the developers really care about. And those that they haven't used for years in other APIs, we kind of brushing them aside, or maybe putting them in extensions if necessary. It's all about creating a very concise and beautiful interface to drive GPUs very efficiently. And then we've translated those philosophies into the core fundamentals that drive Mantle under the hood. And the first of those is us pre-building data structures as early as possible and reusing them as much as possible. It's much cheaper to validate something once at the creation time than to do it on every draw. And then we encourage application developers to do the same thing by pre-building some of the GPU structures and command buffers, and they're using them as much as possible. Then we give you and your applications control over memory management. Again, this is a very key component to achieving very high performance and predictability. Then we also give you ability to directly construct command buffers and submit them. This is also a very important part of Mantle implementation. And at the end, the target is giving you, as a developer and your applications, ability to ultimately control the GPU. You are in control. Effectively, what we are doing, we are putting you, the developer, in the driver's seat. You have all the controls now. You can feel the power, feel the GPU. Now, that's one way to look at it. The other way to look at it is that we are putting you in the driver-developer seat. And let me explain this. For many years, developers have been saying, you guys on the driver's side do not know how to write drivers. Give us all the control and ability to do it. We'll make it much better. And that's what we are doing now. We're getting out of your way. We're giving you a very nice abstraction level, and you can do whatever you think is right to make the best games out there. So this is Brian, you see there. Brian, would you come over here and talk about some of the most exciting features we have in Mantle and explain why it's good for us to give developers all this control?
Thank you, Gennady. Yeah, Gennady said, he hates the small batch problem. I've been a driver developer for 11 years with AMD, and I hate getting in the way of making games, everything they can be. So we're going to try and solve that. Gennady went over the goals for Mantle and its sort of guiding principles as far as the API design. And I'm excited to tell you give you a tour of the main features in Mantle that help us achieve those goals. So one fundamental feature of Mantle is its execution model. And in the spirit of simplicity and getting out of your way, our execution model is based heavily on the execution model of a modern GPU. So in the modern GPU, you have a number of engines that execute commands in parallel. So you have a graphics engine. You can have one or many asynchronous compute engines, or DMA engine, multimedia, whatever. So the basic building block for work for one of these engines is a command buffer. So in this picture, the command buffer is the colored rectangle. The driver builds hardware commands directed at a particular engine, and we put it in an execution queue. The engine we targeted at goes to its execution queue and picks a command buffer off it when it's ready to do work. That's pretty much it. So as opposed to a context-based execution model where the driver is responsible for picking which engine we want to execute something on, for breaking the work up into command buffers, and to synchronizing all the work between the engines, in Mantle, we're exposing abstractions to let the application control of this directly. So the application creates a command buffer, makes driver calls to fill it with commands, puts them in the execution queue, and we have abstractions to manage synchronization between the queues. So by exposing things this way, we give you the ability to take advantage of the whole chip, something like you could do in the console. So what's really important here, though, beyond that, is the fact that you can build command buffers from multiple application threads simultaneously. And that is just the key feature of Mantle as far as achieving scaling with a modern multi-core GPU. So in Mantle, there is no synchronization at the API level. Also, there is no state carryover between the command buffers. So when you create a command buffer, it is up to you to specify all the state. You're responsible for all synchronization of building the command buffer and submitting it. And if you want to use multiple queues, it's up to you to synchronize the work between them. So you get a ton of control to get the best GPU and CPU performance. So as Gennady mentioned before, memory management is another problem in current APIs. And in the current API, when you create an object, such as a texture or a shader or whatever, the driver will implicitly allocate GPU memory for you. And that memory is forever linked to that object. There are a number of problems with this. One is that it's difficult to recycle that memory. If you want to change the contents and have multiple copies of it in flight, that's difficult. You're going to end up with a larger memory footprint, which is undesirable. Creating resources is more expensive because we're always allocating memory with the resource. And you know, that's and the driver also has to manage a lot of OS video memory handles, and that's something that we spend a lot of time doing. So in Mantle, we've sort of broken that relationship. Instead, you create an object, and that object is just a CPU side description of the object, and the GPU memory is separate. The application allocates memory and binds it. So this model solves all the problems that I just mentioned, and we can dig in a little bit deeper to talk about it. So your application actually manages almost all the GPU memory in the whole application. And basically the way it works is you create your object, then you query the driver to say how much memory do I need, what alignment or which heaps does it, should it be in. Then you bind memory to it. And so this opens up a lot of possibilities. If you want to allocate one memory object and then sub-allocate a bunch of little buffers from it, that's great. In fact, we encourage you to do that. If you have a frame where you have multiple scratch images that you're using over the life of the frame, but you never use them at the same time, you can reuse memory to back those images so you can have a smaller memory footprint. We think there's tons of opportunities like that. And another thing I think engine developers will like a lot is that we're offering you the ability to manage the driver's CPU allocations as well. So, we need memory, and we will have callbacks to say, you give us this amount of CPU memory. And that's going to help so that we can integrate with your sub-allocators and get good multi-thread performance in your engine. And this whole memory management thing gives you a lot of power. Mantle is built from the ground up on modern GPU support for virtual memory. And this opens up some feature opportunities, but it also keeps us safe because you can only manage to touch the GPU memory that belongs to your process. And really the whole point of this is that there's only so much GPU memory, and right now you're not getting everything you can out of it. We want you to just squeeze every last bit out of it in the manner that you might on the console. So I sort of mentioned the GPU virtual memory features. One thing Mantle is exporting is the ability to remap pages of virtual address space into real allocations that you've made. So effectively, you create a virtual memory object, which is nothing more than reserved virtual address space. And then you make calls to specify which real allocations you want to back those virtual pages. And this is the mechanism that we base features like partially resident textures on, but we're exposing it sort of at one level down, and we think that there's some cool opportunities, like perhaps flexible content streaming that you could do with this plan. So one area that in the driver we spend a lot of wasted time is draw time validation. And basically in the modern DX11 you can change any of the shader states and a whole bunch of other bind points that you can make per draw. And because modern GPUs sort of have a lot of interconnected dependencies, we, at every draw, more or less, have to go check and see what's bound and figure out how to program the hardware. So in Mantle, we have created the idea of a monolithic pipeline. So in one bind point, you specify all shaders, as well as some amount of fixed function state, which is shader impacting. And the benefit to this is that draw time validation drops to nothing, or very fast. And that's great for CPU performance. It's good for GPU performance too, because we now know everything up front, and we, as the driver, can do some actual driver work and see how we can, optimize, that state for GPU performance, which is kind of what driver wants to do.
Can I ask a question midstream, or should I wait till the end?
I think you should wait to the end if you don't mind.
Okay.
Right. And then the last thing, and I think this is really important, is that for for engine developers, something they really hate, and Gennady mentioned this, is unpredictability. So with the current model, you bind a state that you don't think should matter at all, and then the driver goes off and compiles a new shader because we had to, right? So Mantle's going to be very predictable. You bind the pipeline, it's fast, it's done, no surprises. So despite all the pros I mentioned, there are some cons, and one of those you might wonder about is if there's going to be a combinatorial explosion when you put all of this stuff into one pipeline. And that is something that we're aware of, and we did extensive analysis of modern games, to get a sense for, if we combine this stuff, how many unique pipelines are you as engine developers going to have to manage. And we worked extensively with our ISV partners to come up with just the right balance. So we've managed to keep that in check and get just the most bang for our buck as far as getting the best performance while keeping that number of combinations of pipelines down. And here you can see not everything belongs to the pipeline. Render targets and index buffers and resources don't, as well as dynamic state, which those are the things we separated out, as blending, depth test, that kind of. So something about current APIs is kind of frustrating is all the categories of resources. You have to know, is this an index buffer, context buffer, constant buffer, vertex buffer? Is this a staging resource or a default resource? Some of that's to give the driver a hint about heaps memory belongs in, which we don't have that problem. And other of it, it just has to do with compatibility with legacy hardware. So in Mantle, we're just going to simplify that. And you have memory and you have images. Memory is memory. So whether it has vertex data or index data, it doesn't really matter. Images, we've simplified a lot from textures and other APIs, and particularly they have symmetrical capabilities as far as shader read and write. There are still some cases where it's special case, particularly having to do with depth and color targets, because those still have special purpose fixed function hardware. So now we have those resources. how do we read them from the shader pipeline? And this is an area where Mantle has also tried to innovate some. So we found that the traditional model where you bind resources to particular slots for shader access has turned out to be a pretty big bottleneck in modern games. One alternative that's cropping up a lot now is the bindless model. Bindless solves some issues. It has some issues of its own. It increases shader complexity, arguably stability, and it's certainly less GPU cache friendly. So in our model, we think we can give you the best of both worlds. In Mantle, when you do a draw, you bind a descriptor set that matches the expectations of your pipeline. The descriptor set, at its core, is just an array of slots where you can bind resources, either memory or images. You can also bind another descriptor set to one of those slots. And through that mechanism, you can create arbitrarily complex hierarchies of descriptor sets. So this is good for a bunch of reasons. One is if you have static objects in your engine, you can pre-build your descriptor set one time and reuse it. When you bind it, it's going to be super fast. Even for your dynamic objects, because of the hierarchical nature, you can pre-build as much as you can and just focus on updating the dynamic portions of the descriptor set. And really that's great. It gives the the game developer the opportunity to manage that CPU versus GPU performance trade-off. So the next thing is that you get the ability to bind lots of resources. So it's not quite bindless, but the descriptor sets are arbitrarily big. If you wanted to, you could create one descriptor set with every resource in your whole game, never bind another one. And that's up to you and your trade-off. And then the last and very important is that these descriptor sets can be built in parallel with command buffers. So we're leveraging the multi-core CPU performance. And the last thing I want to talk about is particularly near and dear to my heart as far as driver wasting CPU cycles. And it has to do with tracking resources. So right now, in current API, the driver is responsible for tracking if you bind something as a render target, bind it as texture, and when you switch between those different usages, we need to do work. We may need to stall to prevent the hazard. We may need to flush some caches, driver stuff. There's a bunch of problems with this. One is that most game engines are actually doing this already because they have to do this already for their console support. Another is that the game engine can do a much better job of it because they have a higher order understanding of how their frames are rendered. They're not looking bind, unbind, bind, unbind. They're looking at pass 1, pass 2. And that just makes it a much simpler problem to solve. The third, again, is predictability. With the model where the driver just notices changes and then does work, as an engine developer, you're going to see stalls or cache flushes or even decompresses happening for reasons you can't determine. I just did a draw. Why did it take so long? So those are all things that we're looking to improve in Mantle. Oh, I should also mention that resource tracking is a huge hurdle as far as multi-thread support because it's introduced state that persists across command buffers. So in Mantle, we solve this by not doing it. The application needs to notify us when they change the way that they're using a resource or memory. The application is also responsible for notifying us of hazards, read after write or write after write hazards. So if you render to texture and then bind that texture for shader access, you tell us. If you do back-to-back dispatches with the same memory bound for shader write, that's a write after write hazard, you tell us that as well. So there's no tracking in the driver, but the application can efficiently do it. And I want to really emphasize that this tracking isn't at the level of what the driver does as far as flushing caches and stalls and stuff. It just is you telling us comfortable usages. So this went from shader write to index data. it should be pretty comfortable for the application to do. So this is a quick example. In this example, we draw a triangle to a very literal render target, and then after that, we want to read that image from a shader. So when this happens in Mantle, you will call to notify us that you're switching from render target to shader resource read. The driver, the driver will then be able to insert the commands we need to do, which may be decompression, if the render target is compressed, cache flushes, idles, whatever. But the really important point here is that that preparation is done because the application called to do it. So it can be timed, right? So the application is very aware that this happened, and it gives them the opportunity to optimize it, because they can say, oh, I need to do a bunch of these. Maybe if I do them all at once, I'll insert one bubble instead of multiple bubbles in the pipeline. Maybe they can say, oh, maybe I didn't need to do this at all. It wasn't, that cost just wasn't worth the visual benefit I got. Or maybe they can shrink the resolution of the resource. The whole point is just giving them control and letting them make the best decision to make the best game. So, that's a lot of features, and I think that that's probably enough, right, Gennady?
No, you can always have more, right?
All right, so I'll let you just talk about those then.
All right, so a couple more that we would like to highlight. As I said, excuse me, we have a lot more to make it a lot more compelling platform than any other APIs. And one of the serious problems that games have is the shader compilation time, right? When your game loads, it's quite expensive to compile many shaders. And it seriously impacts load times in the games. And really, there's no need to recompile all the shaders every time a game launches. But also, as Brian said, quite often we would need to kick off a new shader compilation to target a completely different state vector. With Mantle, we give you ability to very quickly and easily save and reload complete compiled pipelines. So this should virtually eliminate all the loading time associated with shader compilation, and as well as make performance a lot more predictable. All these features that we are used to on PC platform due to shader compilation, all of this is gone now. The next interesting thing is that the GCN architecture has a wide range of very advanced MSA features that allow you, as a developer, to balance performance versus quality. And we're including a wide range of those in Mantle. So you can make your games run fast and make them look the best as well. And the last one out of this range of features, I'd like to mention an interesting new innovative feature for very fine-grained task scheduling and execution. But even that is not all. There are still a couple of notable features that elevate Mantle above and beyond other solutions. One of those that I would like to talk about is multi-device operation. With Mantle, the multi-device really is an extension to the native execution model that Brian have talked about. So just to quickly review, this is what execution model looks like. Your application generates command buffers, submits them to different queues for GPU execution. Now, if you look at a multi-device configuration with multiple Mantle devices, it's an extension of a single GPU model. You still build all the command buffers, you see all the individual GPUs, engines, control all the queues, and you synchronize them on those. With synchronization, it'll look to you as an extension of a single GPU model, scaled up to support multiple devices. This should allow you to scale very easily across multiple GPUs without fundamentally changing how your application works. Now, what does this mean? Applications have used all these multi-device features, and in other APIs, it's actually called Crossfire. And we see a lot of games that are using all this alternate frame rendering to achieve greater scaling across multiple GPUs. Now, that alternate frame rendering was fine in the days of DX9 rendering. And DX9 applications scale quite well. Now, if you take a compute or other complex tasks that have frame-to-frame dependency, this is where you start seeing alternate frame rendering fall apart. Why? Because to solve this dependency, either you have to duplicate your work across the GPUs, or you serialize between the GPUs. In any case, the scaling suffers. And up until now, we've managed reasonable scaling. And it was mainly due to DX9 style of games, mainly driven by the previous gen of consoles. Now, with GCN architecture and its support for compute, we are starting to see a trend where a lot more games are going towards more compute workloads. So what do you do now? With Mantle, we are uniquely positioned to give you control, to partition the workloads in a way that really makes sense for your application, and make it scale in a very flexible way for these new workloads. And more importantly, it allows us to target all these asymmetric configurations that are becoming more and more important. In a keynote, Lisa mentioned some numbers, how many APUs we have out there, and we are talking about hundreds of millions of those. So if you think about it, a combo of APU plus high-end GPU is actually much bigger market than conventional Crossfire market. This is a market that's actually very important to you and your users. And the big problem with asymmetric configurations, if you try to do AFR, it does not make sense. It actually makes it behave a lot worse than if you're running just APU or discrete GPU, just because of the disparity in compute power in those devices. Now, what you could do is actually implement much better scaling by adjusting the workloads where they make sense. And I'll give you a couple of examples, but the important part is that really we're giving you all the tools necessary to unlock all these interesting new scenarios, usage scenarios, compute, and so forth, on a wide range of targets, including all these interesting asymmetric configurations. So I'll give you a couple of examples of the use modes. In case of multiple GPUs, let's say we have a couple of discrete cards. You can maybe use one card for your main scene rendering. Just do very, very fast scene rendering for low latency and fast frame rate, while you would use another GPU for some other compute-based, slower changing tasks that are not really that scene rendering affecting. So something like GI, global illumination. This gives you best performance and best visuals, something you could never achieve with just a simple AFR. And for the asymmetric configurations, maybe your APU graphics could be used for a general coprocessor for your game. Maybe you'll run physics or AI or some other compute-based tasks. Or maybe if display is attached to it, maybe you'll use it for final frame post-processing, while the main rendering is done on a discrete GPU. Really, it's up to you. I'm sure you'll find out much more interesting, compelling scenarios. This is just a couple of examples. Now, the last thing I would like to cover is debugging capabilities in Mantle. And we hear you guys on development side. Tools are very important to you. So we've taken it extremely seriously, and we've put a lot of the effort into making it a part of our driver and the API. We are building a lot of validation and debugging capabilities right into Mantle. So in many cases, building tools on top of Mantle wouldn't be much more than building a fancy UI on top of what we have already. And because we're adding a lot of this extra validation, we're giving you a lot more control so you can trade safety versus performance. And you can run for a bit, then you can enable more validation to debug very specific parts in the game where it matters. And of course, we're adding more innovative features. So we are adding a lot more control for stress testing applications, for emulating all kinds of debug scenarios, something that you've never seen before in other APIs. We're really putting a lot more emphasis on debugging and validation right at the core of it. So we are building an API from the ground up based on the feedback and with the help of developers like you. And actually, there are a lot of benefits. We are trying to take into account as well the changes to the gaming and PC ecosystem, all these recent trends that are happening. One of those is that with Mantle, we uniquely positioned to empower lower end configurations. And this aligns extremely well with the general trend of the whole industry towards lower power devices. These are devices in the most need for efficient solution to drive them. And Mantle is that solution for very constrained power or performance environments, mainly for the efficiency reasons. We are very lean and mean driver, very predictable in terms of its operation, and that gives great performance and predictability to the applications. Again, something that developers have been asking us for the very, very long time. Also, because GCN architecture unifies a large portion of the console market with a large portion of the PC market, Mantle on PC gives a unique feature set to bridge those platforms and bring optimizations from one platform to another. This is the easiest way to transfer your applications between those platforms. And of course, as I said, in the beginning, we're trying to really kick it up a notch for the whole industry. We really would like to spark another round of innovation through introduction of new API and get everybody excited again. There are a lot more that can be done. I'll just quickly mention one thing, that this is not just about performance. Please look beyond that. Because we're not targeting 2x or 3x performance, or 20% performance, right? The big question is, once I am completely in an open field, where can I go? What new genre of games or gaming scenarios or techniques, maybe it's shadows, maybe it's global illumination, that can be unlocked with this never before seen performance. Now, I am sure that you would like to find out more. We're actually going to be launching a closed beta program in the next couple of months. And in the meantime, if you're interested, please talk to your friendly AMD ISV representatives. All your account managers, all your support engineers, and I'm sure they can help you to figure out how to deal with beta program and where you go forward. And of course, see more of cool presentations today. There's going to be a keynote from DICE, and there's going to be a presentation from Oxide. These are the guys who had a chance to actually play with the real API, and they have a lot of interesting insight to share with you. So make sure you attend those talks. All right? Now, before I wrap up and we go to the questions, I'd like to say a big thank you to the whole Mantle development team, all these guys who have worked very hard to make this happen. And I'm not going to put any names on the slides because I don't want recruiters out there to steal the best driver engineers that AMD has. Thank you, guys.